All right, let's take a deeper dive into other aromatic compounds. So let's review. An aromatic compound has to fulfill two criteria. First of all, you have to have a fully conjugated ring with overlapping p orbitals. So that means we have to have a continuously overlapping system of p orbitals in our ring. And the second thing is it has to satisfy Huckel's rule, which means we have an odd number of electron pairs, 1, 3, 5, 7, etc., or 4n plus 2 total pi electrons where n is equal to 0, 1, 2, 3, 4, 5, 6, etc., etc. Now, for an anti-aromatic compound, those have to fulfill two criteria. Number one, you have to have the same old fully conjugated ring with overlapping p orbitals. So again, a completely overlapping system of p orbitals. But in this case, we have an even number of electron pairs, or 4n total pi electrons, where n is equal to 0, 1, 2, 3, 4, etc. Now, if you have a compound and it fails criteria number one, so let's say you have an sp3 hybridized carbon in your ring, so you don't have a continuously overlapping system of p orbitals. In that case, it's non-aromatic, okay? And the abbreviations, like you saw before, for aromatic, I like to just use A. For anti-aromatic, I use AA. And for non-aromatic, I put NA, like that. Now, it turns out that there are actually very few anti-aromatic compounds, but all of the compounds that you see on here are anti-aromatic, meaning they have a continuously overlapping system of p orbitals in a fully conjugated system. That's a ring, okay? But we have some kind of 4n number of electrons where n could be 0, 1, 2, 3, 4, etc., etc. And so these are some anti-aromatic compounds. And so we have this cyclopentadiene carbocation here. So again, remember that when you have a carbocation, this carbon is sp2 hybridized, therefore it has an unhybridized p orbital on it. So here you can clearly see we have a continuously overlapping system of p orbitals. But how many pi electrons do we have? 1, 2, 3, 4. So that's a 4n number where n is equal to 1, right? Over here, the same thing. In order for these electrons to participate in resonance, right, they have to be in a p orbital, okay? And so in that case, we'd have 1, 2, 3, 4 pi electrons, or electrons in that those p orbitals. And so that would be an anti-aromatic compound. The same thing with our cyclobutadiene, anti-aromatic compound. And then we have this compound over here, which would be an anti-aromatic compound as well. And so each of these unusually unstable molecules is cyclic, conjugated, and flat, okay? And we saw that with the cyclooctatetraene, that it is not anti-aromatic, that it's actually non-aromatic because it adopts the tub shape that we saw earlier on. And so again, there are actually very few anti-aromatic compounds, so it's not a bad idea to familiarize yourself with these compounds as being anti-aromatic compounds. Now the next slide here shows you what are called annulenes, and annulenes are nothing more than rings that are fully conjugated, okay? And so the first one is 6-annuline, and you're like, well, I recognize that compound, that's benzene. I agree, that's just benzene. And obviously that is an aromatic compound, so we'll put A above it. It's aromatic because it has a fully conjugated system in a ring, and it has a total of 6 pi electrons, 6 pi electrons total, so that's 3 pair. 3 is an odd number, so it satisfies Huckel's rule. And there we go, so everything's good. If you go to 10-annuline though, 10-annuline, you might think, hey, that's perfect too, because I have a continuously overlapping system of p orbitals, right? Every carbon in here is sp2 hybridized. Okay, good. We have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 4n plus 2 when n is equal to 2. So you're saying, well, that's a Huckel number, so that's good. So this should be an aromatic compound. It turns out that 10-annuline is actually a non-aromatic compound. Now, if you're asking, now, why would that be? Well, if you remember that in order for a compound to be aromatic, it has to be planar or flat. And we have 2 protons. There's one here, and it's even hard to draw the second one. There's 2 protons in the middle here. And these protons cause a steric hindrance to occur here in the middle of the ring. And this pushes the ring out of planarity. And so it doesn't overlap, or those p orbitals don't overlap efficiently. And so it's actually non-planar. And so it's considered to be a non-aromatic compound. Now, when you get to 14-aniline, you might think, okay, well, I have protons sticking out inside like this that would push this compound out of planarity. And even though it does have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 is 4n plus 2 when n is equal to 3. 3 times 4 is 12. Plus 2 gives you 14. You might think this should be an aromatic compound. And it is aromatic. And even though you have those protons sticking out in the middle, it's still an aromatic compound because even though it does deviate from planarity a little bit, the deviation from planarity is not too great. And then if you go to 18-aniline, which isn't even shown on here, it's found to be nearly planar and therefore aromatic as you would expect it to be. And so the conclusion is benzene would be aromatic, 10-aniline non-aromatic. Why? Because it's not planar. And then 14-aniline is not perfectly planar, but it's not out of planarity enough to make it non-aromatic. So it would be considered, it would be considered to be aromatic. And then if we had 18-aniline, it would be aromatic as well. Now, previously, we looked at molecular orbital theory in Frost circles to explain the requirement for a Huckel number of pi electrons. Now, let's take a look at a Frost circle of a 5-membered ring. And you can see here that with our 5-membered ring in our Frost circle, if we had a total of 1, 2, 3, 4, 5, 6 electrons in here, we would end up with something that's aromatic. Now, if you're thinking, well, how would I incorporate 6 electrons into a ring that only has 5 carbons in the ring? And the way we do that is by making an anion. And that anion is what we call the cyclopentadienyl anion. And this is another compound you have to memorize. The cyclopentadienyl anion is in fact aromatic. Now, why would that be? Let's take a look at it, okay? If we take a look at this anion right here, you see that we have 1, 2, 3, 4 pi electrons here, okay? No argument there. But what about this lone pair here? What kind of orbital is it sitting in? Well, remember, in order for that lone pair to participate in resonance, as is shown here, throughout all 5 of these resonance contributors, it must be inside a p orbital. And so that tells you that you have a p orbital, and just forgive me for my lackluster drawing, you've got a p orbital on every single one of these carbons. So we have a continuously overlapping system of p orbitals. So that's good. And we have a total of 1, 2, 3, 4, 5, 6 pi electrons that are involved in resonance throughout this continuously overlapping system of p orbitals. Is that a Huckel number? Yes, it's 4n plus 2 when n is equal to 1. 4 times 1 is 4, plus 2 gives you 6. And we have a total of 6 electrons. Again, you can look at the next contributor. 1, 2, 3, 4, 5, 6. And so the cyclopentadienyl anion is in fact an aromatic anion, and you want to memorize this anion, okay? It's an anion that you should memorize. Now, what's interesting about this is if you think of the acidity of a hydrogen on a carbon, on an sp3 hybridized carbon-hydrogen bond, okay? Like let's say you had something like cyclopentane, okay? If you had cyclopentane, and if you were to look at the pK of this proton, it's going to be around 50. Okay, it's going to have a very high pKa, not acidic at all. But if you look at cyclopentadiene, it has a pK of 16. It's pretty close to that of an alcohol. Why is it so low? Why is this proton so acidic? Well, the rationale is this. The reason why that proton is so acidic is because once you remove it, you go from something that is non-aromatic to something that is aromatic. And what does aromatic mean? It means something that's highly stabilized. Again, if you're looking at this compound and saying, why is this non-aromatic? The reason why it's not aromatic is because this carbon is sp3 hybridized. It doesn't have a continuously overlapping system of p orbitals. Now, if we look at the Frost circle of a 7-membered ring, again, we can see that if we had a total of 1, 2, 3, 4, 5, 6 electrons in our Frost circle for our 7-membered ring, okay, then we could have something that's aromatic. Well, how would we do that? The way we do that is one of the carbon atoms is going to have an empty p orbital, and therefore the compound is going to have to be a cation and not an anion. And that cation has a name. It's called a tropylium cation. And again, I highly recommend that you memorize the tropylium cation. Take a look at the tropylium cation. You can see it's got a total of 7 resonance forms. Look at this. Remember, a carbocation is sp2 hybridized, so therefore there is a p orbital on here. There's one on here, there's one on here, 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 and here. So do we have a continuously overlapping system of p orbitals? Absolutely we do. How many electrons do we have? 1, 2, 3, 4, 5, 6. That's a Huckel number. So does the tropylium cation meet the criteria for being aromatic? The answer is absolutely. And so you have to know the cyclopentadienyl anion and the tropylium cation are both aromatic for different reasons, but they're both aromatic compounds. Now, cyclic compounds containing heteroatoms like sulfur, nitrogen, or oxygen, we call these heterocycles. And a couple of examples of heterocycles that are of interest to us are pyridine and pyrrole. And to round out these Lewis structures, we should put the lone pair on the nitrogen here and the lone pair on the nitrogen there. Now, both of these compounds are aromatic. Pyridine is aromatic and pyrrole is aromatic, but for very different reasons. If we take a look at pyridine, which is shown down here, pyridine exhibits a continuous system of overlapping p orbitals, and therefore you can see with this overlapping system of p orbitals down here and down here, it satisfies the first criteria for aromaticity. Now, the nitrogen on our pyridine is sp2 hybridized, and the lone pair on the nitrogen occupies an sp2 hybridized orbital, which is pointing away from the ring. The lone pair, meaning this lone pair, this one right here, is not part of the conjugated system of the ring, and therefore we don't count it when we're counting up the total number of pi electrons. So in this case, we have a total of 1, 2, 3, 4, 5, 6 pi electrons. And therefore, pyridine is an aromatic compound. Now, since the lone pair on the nitrogen in pyridine doesn't participate in resonance or aromaticity, it means that pyridine can function as a base or a proton acceptor. And we see that right here. When pyridine accepts a proton, it goes from being an aromatic compound to still an aromatic compound when we make a pyridinium ion. So pyridinium ion would be the name of this cation here. So again, pyridine is a base. Why? Because the lone pair has nothing to do with aromaticity in this specific case. Now if we take a look at pyrrole, again, the nitrogen atom is sp2 hybridized, but in this case, the lone pair is in a p orbital. In order for the pyrrole ring to achieve a continuous system of overlapping p orbitals, the lone pair on the nitrogen must occupy a p orbital. Recall that way back in the beginning of Organic Chemistry 1, that a lone pair occupies a p orbital if it's participating in resonance. So, with 6 pi electrons, 4 from the 2 pi bonds, 1, 2, 3, 4, and 2 from the lone pair that's on the nitrogen, this makes pyrrole an aromatic compound. However, in the case of pyrrole, unlike pyridine, the lone pair is crucial to keep for the compound to be aromatic. The delocalized nature of the lone pair on pyrrole, the delocalized nature of the lone pair on the nitrogen of pyrrole explains why the nitrogen in pyrrole doesn't function as a base. Check it out. If pyrrole was to accept the proton, we go from pyrrole, which is aromatic, and if we were to make a pyrrolidinium ion, I guess is what this would be called, it becomes non-aromatic. So now we have something that's non-aromatic. Well, why is it non-aromatic? Because now this nitrogen is sp3 hybridized. It has no p orbital. And so the difference between pyridine and pyrrole can be seen by comparing these two electrostatic potential maps that you see here on the screen. In general, we don't like to compare electrostatic potential maps. However, since these two are using the same color scale, it's okay for us to do that. And the reason why is because the lone pair is not part of the aromatic system, and therefore that lone pair is free to function as a base. Now, if we take a look at the electrostatic potential map of pyrrole, in this case, the lone pair is delocalized throughout the ring, and the nitrogen atom does not represent a site of high electron density. And so we see that the electron density is spread throughout the entire molecule. All right, so let's take a look at this question, and it asks us to determine whether the following compounds are aromatic, non-aromatic, or anti-aromatic. So we'll use A for aromatic, we'll use Na for non-aromatic, and we'll use AA for anti-aromatic. Well, if we start out with A, this anion here, sorry it's a little blurry, but we know that this lone pair could participate in resonance like this, and you could spend the time drawing all the resonance forms if you wanted to. And so the only way that that lone pair can participate in resonance is if it's in a p orbital. And so we have a continuously overlapping system of p orbitals because the lone pair can participate in resonance. This carbon and this carbon are both sp2 hybridized, so obviously they have a p orbital on them. So we have our continuously overlapping system of p orbitals, but here the number of electrons is not a Huckel number, right? We have 1, 2, 3, 4, which is not a 4n plus 2. This is a 4n where n is equal to 1, right? 4 times 1 gives you 4, and therefore this compound is going to be anti-aromatic. And so we could add that compound to our list of anti-aromatics that we had in this previous slide. Now if we look at B, again I'll have to zoom in here, we see the carbon that has the carbocation, that's sp2 hybridized, so therefore it has a p orbital, as do these carbons here, so we have a continuously overlapping system of p orbitals. That's good, and we have a Huckel number of electrons, right? Or Huckel number of pi electrons, I should say, 1, 2, so that's 4n plus 2, where n is equal to 0. So 4 times 0 is 0, plus 2 gives you 2. So there you go. And so this compound would be aromatic. Now the next one is this cyclopentadienyl cation. And so remember, when you have a carbocation, it's sp2 hybridized, so there's a p orbital on there. There's a p orbital on all 4 of these carbons that I have highlighted in blue. So we have a continuously overlapping system of p orbitals. But do we have a Huckel number of pi electrons? 1, 2, 3, 4. No. This is 4n, where n is equal to 1. 4 times 1 is 4, and therefore this would be an anti-aromatic compound. And if you go back to that slide of anti-aromatic compounds that I had, you'll remember that this was the first compound on there. Now, if we look at D, you notice that the lone pair can participate in resonance. You could draw all kinds of resonance forms for this guy. And so in order for that lone pair to participate in resonance, it has to be in a p orbital. Every other carbon in here is sp2 hybridized. So do we have a continuously overlapping system of p orbitals? The answer is yes. How many total pi electrons do we have? Let's tally them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that a Huckel number? The answer is yes. It satisfies 4n plus 2. When n is equal to 2, 2 times 4 is 8, plus 2 gives you 10. And so therefore this anion would be aromatic. Okay, in 17.13, we're asked to determine which, if any, of the lone pairs are participating in aromaticity. So if we take a look at this first compound, I'll just redraw it like this maybe. Okay. Now, could one of those lone pairs participate in resonance? The answer is yes. Okay. So if it did participate in resonance, remember, it would have to be in a p orbital. And so that would mean that the oxygen would have to be sp2 hybridized, right? Because it would have a total of 1, 2, 3 regions of electron density if we were to form the resonance form here. So that means that one of the lone pairs could participate in resonance. Now, would it do that? Would it participate in resonance to make the compound aromatic? And the answer is yes, because if it did, we'd have a continuously overlapping system of p orbitals, and we would have 1, 2, 3, 4, 5, 6 total electrons participating in resonance, which is a Huckel number, 4n plus 2, when n is equal to 1, and therefore the answer is yes. Yes, this lone pair would be participating in resonance. And thus, this compound would be aromatic. Now, the next compound, we call this thiophene. This compound, One of the lone pairs occupies a p orbital, again, thereby rendering the compound aromatic because it has a total of 6 pi electrons. The other lone pair would occupy an sp2 hybrid orbital in the plane of the ring, extending away from the ring. So again, this compound would also be aromatic. Now in C, we'll just zoom in here and think about this. If this lone pair was in a p orbital, then you would have a continuously overlapping system of p orbitals, but you'd have an anti-aromatic compound because you'd have an even number of pairs of pi electrons, right? You'd have 4n, where n is equal to 2. 2 times 4 gives you 8. Okay, so that would be anti-aromatic. So remember, a compound will do whatever it can to avoid being anti-aromatic. I told you there's actually very few anti-aromatic compounds. And so to avoid the instability associated with anti-aromaticity, the lone pair is expected to occupy an sp3 hybridized orbital. Again, we have 1, 2, 3, 4 regions of electron density. And so since the nitrogen would be sp3 hybridized, this would be a non-aromatic compound. In D, one of the lone pairs on sulfur is going to occupy a p orbital, thereby rendering the compound aromatic because we'd have a total of 1, 2, 3, 4, 5, 6 pi electrons like that. Now the lone pair on the nitrogen already occupies an sp2 hybrid orbital that is in the plane of the ring because the nitrogen atom is already using a p orbital as part of the pi bond to establish aromaticity. So yes, the lone pair that I have highlighted in yellow would participate in resonance and therefore it is required for aromaticity, and this would in fact be an aromatic compound. And then finally in E, there's only one lone pair on the oxygen, and it's not required for aromaticity. It's not participating in resonance in this case. And so the oxygen atom is already using the p orbital as part of a pi bond to establish aromaticity. And so this lone pair has nothing to do with aromaticity, but this compound would be aromatic. Now Huckel's rule is meant to be applied for a single ring of p orbitals. Nevertheless, many polycyclic aromatic hydrocarbons, or PAHs, are known to be stable and have been thoroughly studied. We have 3 here. It might not be a bad idea to commit their names to memory: naphthalene, anthracene, and phenanthrene, shown here. Now these compounds are comprised of fused benzene-like rings, and they exhibit significant aromatic stabilization. For each compound, the stabilization energy can be measured by comparing the heats of hydrogenation, just like we did for benzene. These values are summarized in the table that you see here. For polycyclic aromatic hydrocarbons, the stabilization energy per ring is dependent on the structure of the compound and is generally less than the stabilization energy of benzene, as we see here. You see the benzene has the highest and the other ones are lower. In addition, the individual rings of a polycyclic aromatic hydrocarbon will often exhibit different levels of stabilization. For example, the middle ring in anthracene is known to be more reactive than either of the outer rings.